Welcome back. As I had noted, it will be important to master the normal probability distribution because we will be using it intensively from this point onward. This is the formula for the normal probability distribution. As you will see, all the parameters you need are the mean and the standard deviation, which you then plug into the formula, which also contains pi and e. Fortunately, there are ready-to-use tables, especially the ones behind the covers of your textbook. Here are some features of the normal distribution. It is symmetric, or technically, we say that its skewness measure is 0. That is, the right-hand side looks exactly like the mirror image of the left-hand side. And as I said, these are all we need to know about the normal distribution. Once you know the mean and the standard deviation, you're ready to go, and you can make inferences and all other calculations. The highest point on the normal curve is the mean, and it also happens to be the median and the mode. Please take a minute to think about that and its implications. The mean can be any value. It can be negative, 0, or positive. What about the standard standard deviation? What do you think can its values be? As you recall from chapters 3 and 4, the standard deviation can only be positive. Now about the standard deviation, it determines the width of the curve. The larger the standard deviation, the wider and the flatter will be the curve. What this means is that extreme values are more likely when the standard deviation is high. The probabilities are given by areas under the curve. This is true of all continuous random variables. And because the normal distribution is symmetric, the area under the curve will be 0.5 to the left of the mean and 0.5 to the right. But as you will note, they should add up, and they do add up to 1. Now these are important things to note about the normal deviation and normal distribution based on the empirical rule. Please take a minute or two to read these. 68.26% of the values will be within plus or 1 standard deviation from the mean. 95.44% will be between plus or minus 2 standard deviations, and 99.72% will be within plus or minus 3 standard deviations. Concretely, what does this mean? Suppose a population has a mean income 10 and standard deviation 2. Then we immediately know from the previous slide that 68.26% of the population will have incomes between 8 and 12. Why? Because the standard deviation is 2. Hence, 1 standard deviation is 2. Hence, the people to the right and to the left of the mean, specifically 2 more than the mean and 2 less than the mean, which means therefore a range of 8 and 12. That means 68.26% of the population will be within that range. Similarly, following from the previous slide, 95.44% of the population will be between plus or minus 2 standard deviations from the mean. Remember, the standard deviation is 2. Hence, 2 standard deviations is 4. 4 plus 10 is 14. 10 minus 4 is 6. And that is why between 6 and 14 you will find 95.44% of the population. Please take a moment to calculate for yourself and see why 99.72% will have incomes between 4 and 16. This is just the graphical depiction of the empirical rule that we have described, and illustrated. What is the standard normal probability distribution? It is just a special case of the normal distribution. It is a normal distribution where the mean is 0 and the standard deviation is 1. What is so nice about the standard normal probability distribution is that any variable, and I mean any variable that is normally distributed, we can convert to a standard normal. And once we've converted it, we can then use the tables, the basic tables that we will find in any statistics textbook. This is what we use to designate the standard normal random variable. We say Z. As you will see from the picture, the mean is 0, the standard deviation is 1. How do we convert? We use this formula. Z equals whatever is the value of the normally distributed variable that you have, x. Subtract the mu from it, i.e. the mean of the normal variable, and divide it by its own standard deviation. By so doing, you have translated the normal variable into a standard normal variable. We can think of Z as a measure of the number of standard deviations x is from its own mu. For instance, please read the example. Pepzone sells oil. When the stock of oil drops to 20 gallons, the store orders a replenishment. Now the store manager is concerned that sales are being lost to stockouts, i.e. they do not have enough oil to meet their customers' needs. It has been determined that the demand is normally distributed with a mean of 15 gallons and a standard deviation of 6 gallons. So now we know it's normally distributed. Now the manager would like to know what is the probability that demand will exceed 20 gallons. Because when it exceeds 20 gallons, then they will not have enough oil on hand to meet their customers' needs. So they need to be able to anticipate this. Mathematically, this just says what is the probability that x is greater than 20. Please pay careful attention to how we obtain this probability. First, we convert 20, a normal variable, to a standard normal variable. Hence, plug in 20, plug in 15, which is its mean, and plug in 6 into the formula for calculating the standard normal. As you will see, this means that a normal variable of 20 with mean 16 and standard deviation 6 is the same as a standard normal with a value 0.83. Next, find the area under the standard normal curve to the left of z equals 0.83. This is important, to the left. Please turn to the next slide. How do you use the table? Look in the column, the rightmost column for 0.8. Then look in the topmost row for 0.03, where the two intersect. In this case, the number 0.7967. That gives you the probability that z is less than 0.83. Less than or equal to 0.83 is also the same, because with the continuous variables, an exact value is not really meaningful. So, please take a moment and think. The probability that z is less than or equal to 0.83, what is that equivalent to in terms of x? Before we answer that, let's first calculate this. If we know what the probability is that z will be less than or equal to 0.83, which in this case is 0.7967, then the complement of that is z being greater than 0.83. And what is the probability of z being greater than 0.83? It's just 1 minus the probability of z being less than or equal to 0.83. And hence it's 0.2033. But think about this. That's also the same as the probability of x being greater than 20. Hence, we have answered our question. What is the probability of a stock out? That is, what is the probability that demand will be greater than 20 gallons? It's 20.33%. To recapitulate, we converted the x of 20 to a z value of 0.83. We then used the standard normal table to find the probability that z will be less than or equal to 0.83. But that's just the same as calculating the probability that x is less than or equal to 20. Hence, if the probability that z is less than or equal to 0.83 is 0.7967, that's the same as calculating the probability that x is less than or equal to 20. And therefore, the probability that x is greater than 20 is just 1 minus the probability that x is less than or equal to 20. And after all that calculation, we get the same 20.33%. And graphically, this is what we've been doing. We converted x to a z of 0.83. We used the table to get the area 0.7967. And therefore, the remainder of the area under the curve is 0.2033.